We're going to talk about thunderstorms, which has happened to be my favorite topic, and tornadoes today. One of the things I really want to do is try to put this into terms of what you can see on a day-to-day event. So let's just delve into thunderstorms first. Basically, we've talked about parcels of air rising. So here you have an air parcel rising on the left-hand side. 3 to 5 miles across, all the air is going up, developing a towering cumulus cloud. At some point, enough air has gone up, it's cooled enough, and you begin to get the condensation and you get rain. Well, with that, you wind up with an area of wind that starts to come back down with that precipitation. So you wind up with area of wind coming up and wind coming down. This, in the northern hemisphere, the updraft is normally on the east side of the storm. Most of our moisture comes from the Gulf of Mexico or the Atlantic. So where those are located relative to the storm is typically where the updraft is going to want to be. And most of the weather comes from west to east. And eventually, all the air is going up, and this whole thing gradually drops off. Rain keeps falling, but it's gradually less and less clouds. So there are various types of thunderstorms. We have a single cell, which is what we just looked at. They tend to last anywhere from 20 to 45 minutes. They're done. And that is your typical thunderstorm in the summertime. You'll get one thunderstorm, maybe over your house or maybe over your neighbor's house. And it'll last, it'll linger for a little bit, move a little bit, and then die out. When you get a multi-cluster, you have a better chance for severe weather. Single cell, you're not going to usually get it. Or you get a line. And then you find up with the supercell. They're the most intense thunderstorms. So each one of these is dictated by stability or unstable atmosphere and wind shear. So here you can see a multi-cell cluster. The cell movement is to the northeast, but there is always a new cell forming on the southern end of this line. So because of that, that new cell, which moved up to here, but there's been another new cell and another new cell. So the actual line of storms continues to the east or southeast if you pushed it that way. It just depends on the orientation. It is because of the new cells that are continually forming that the line doesn't move the same direction as the individual cells. So they're related to each other. Conditions got to be right. You got to have a humid air mass, kind of maritime tropical, have some instability and some kind of uplift. Usually a front. Sometimes it might just be a mountain range. Maybe it's a sea breeze. And solar heating definitely drives the convection. So your maximums are typically in the afternoon and evening hours. And here you can see the map of the most thunderstorms. Florida has the most. However, you get it, decent amount up in Ohio, lesser amounts in New England, and not too much out in California, but there are some. So why does Florida get the most? Well, you think about it, they're almost always in a maritime tropical air mass. They have the Gulf of Mexico on one side and warm Atlantic on the other. It is hard for them to get a cold front to go through there, except maybe in the wintertime, once in a while. Otherwise than that, they're going to be in a very moist tropical air mass, and you have a sea breeze on the Gulf of Mexico side, and you have a sea breeze on the Atlantic side. Guess what? They come together. They can, depending on which one is stronger, there's a line of thunderstorms that develops and moves with those sea breezes each and every day, pretty much starting about June 1st and ending in September. They can start earlier than that, too, some years. Severe thunderstorms are really related to wind shear. What is wind shear? Wind shear is a change in direction or speed with height of wind. So all we're saying is that if you could go up a mountain, say the wind shear was coming wind is coming out of the southwest at the bottom of the mountain. By the time you got 5,000 feet up, the wind was coming out of the northwest. That's wind shear. The wind went from southwest to northwest as you were going up. Most severe thunderstorms in the Midwest, this is the classic case. And might as well kind of give you an example of a classic case that we had just the other day. The other day we had Storm Prediction Center issued a high risk, and I mentioned it. And I pointed it out a little bit in this discussion. But you can see, here's the thunderstorms, tornadoes that have occurred. There were actually 47 tornado reports, 101 wind reports, 49 hail reports, 197 reports of damage in this one day. So if you were to look at this day, and around 0Z is when the atmosphere got going, what do you see? You got the southerly wind. Well, just what we looked at. Nice strong southerly wind too, 45 knots. All kind of moisture. The green is basically dew points above, I think it's 12 degrees Celsius. So it's fairly moist air. We have 18 degrees Celsius down here all coming in. So there's lots of moisture being fed up into this system. So if you want, notice the southerly winds too. Now let's go up to 700 millibars. Winds have turned a little bit southwesterly, haven't they? And if you go up to 500 millibars, they're now southwest, and they're really blowing. Some of these winds out here are 75 knots. So they're very strong winds from the southwest. You have very good wind shear over that. One other thing to look at maybe would be look at this. Southwest winds here. Look at the divergence in the yellow here. Tremendous divergence right over that area. So now there's a cold front coming through, and there's a warm front lifting north. We have lift from those. We have lift from divergence. We have wind shear. Final thing, what about a sounding? Well, let's take a look at a sounding. Right in the middle of it, the air that's coming in, Lake Charles, Louisiana. What do you see? This is the amount of instability in that sounding. Anything that the air is to the left of that, that is all air parcels will be coming up to the right of that. This is, if you took an air parcel from down at the ground and lifted it up moist adiabatically, it would be staying right here. Notice the temperature difference. That is a lot of temperature difference right here. So this whole area is called convective available potential energy, CAPE. There is tremendous instability down here. Look at the wind shear. It's all south-southwest, turning more westerly, but definitely increasing with height. So you have more and more wind shear. This is a classic example of tornadoes. So it really does look very much like that. So if we were to continue on, one other thing that's interesting about severe weather, you want to get it as hot as possible. So what you really want is a little bit of an inversion somewhere in that sounding that doesn't allow clouds to develop too much. So eventually you break that inversion, but by then it's gotten so warm that you really shoot the air upwards much faster. Sometimes within clouds we get lightning. Lightning is a lot of fun because it's not easy to understand, to grasp why lightning occurs. There are ice crystals called graupel. They're kind of part ice, part liquid, and they descend, go up in the cloud or go down in the cloud depending on what's the wind direction in the cloud is or how much they weigh. They're very small, and if their temperature is less than 5 degrees Fahrenheit, they're negatively charged. But if they're greater than 5 degrees Fahrenheit, they become positively charged. So guess what? The higher up in the cloud, the more negative they are, and the ice crystals around them become positively charged. On the other hand, down at the bottom, they become positively charged, and they're negatively charged ice crystals. And you can see this separates two different charges, positive, negative, and you wind up starting getting lightning from these charges. So this is how lightning formed in a cloud. Because grapple changes polarity, changes from plus to minus within temperatures, you wind up developing lightning within the cloud. Another problem with thunderstorms is the downdraft, very strong downdrafts along an airline path. There have been too many aircraft accidents based on this. So what happens is, along a path, and it may only be 3 miles long, very short distance, you have winds being pushed down out of the sky, out of the thunderstorm cloud, or even a small towering cumulus cloud. They hit the ground and they spread out. So if a plane's coming in and hits into this strong wind, all of a sudden has a pretty good lift. So the pilot, wants to stay on the glide path, so it's trying to compensate, push it downward. And all of a sudden, on the other hand, you get out of that downdraft, out of that wind, and you go down, you wind up going down to below the down glide path very quickly, and you may be dealing with a crash. Unfortunately, the stronger that wind is, the more dangerous they are. All right, here's a derecho. Let's talk about them for a second here. You've all mentioned derechos at times, and I wanted to show you. This was a classic one. It occurred in 2012, June 29th and 30th. It originated all the way back in Iowa and wound up all the way at my house. Literally, I had damage. I had a tree down in my yard from this. There were numerous trees down across parts of Ohio, West Virginia. Matter of fact, most of the state of West Virginia was without power. A lot of Virginia had no power. So what happened with this? Area of thunderstorms developed back in Iowa. Around 2 o'clock, it had moved just east of Chicago. Right here it is. Not real big, is it? But that area of thunderstorms continued to grow, and notice the wind speeds. 91, 64, 84, 80. Look at how it's bowing across Ohio. 81 mile an hour winds. 68, 59, 70 mile an hour winds here as it's coming through West Virginia at 8 o'clock at night. It finally gets over to my house about midnight, and it's 66 mile an hour winds. Still, all the way, it originated back here. Derechos happen where lines developing thunderstorms spread out into a very fast-moving line from the west to the east. They got to travel long distances. And that was the classic with this one. This is one of the most classic ones around. There have been bigger ones. There have been some that have had over 100 mile an hour. So, one of the main things with thunderstorms hazards, and let's just take a look at this quickly here. You have an ordinary thunderstorm, but if it grows, more thunderstorms develop in this area, it becomes multicellular. And you wind up getting this like a comma at the top and all the way down here along this line with very bowing outwards here. You get very strong winds in this area. And that's what happened with this derecho we had. And you can see here, these are some reports of high winds with that one. Another issue, think about it, thunderstorms pull in lots of moisture. If they keep reforming over the same area, because they're so high, because there's so much precipitation occurring, they're going to cause flash flooding. And that's what can happen, and did happen in some cases. One of the things about flash flooding, it talks about the Big Thompson Canyon flood. I actually lost a friend in that flood. Instead of trying to climb up the hillside, which would have only been about 20 feet, they had to go up. They chose to try to drive out of the canyon ahead of the water They lost. They were drowned their car went over one of the bridges that was on the Big Compton Canyon at the time. And I've since been out and looked at that. It's an amazing sight to see where the water came through that canyon. So if you ever get caught in a flash flood, try to go up. Even if it means climbing a tree, probably you'll have a better chance than trying to outrun it. Another damage things from thunderstorms are hail. They can get quite large. And one of the interesting things with hailstones now is we consider damaging hail to be 1 inch in diameter or quarter size. Anything less than that is not considered severe anymore, even though I've seen lots of it cause some problems. But what happens is, think about it, the air is an updraft, pulling raindrops upward. Literally, they become frozen at some point. They come back down because we saw that there's a downdraft as well. But they're probably coming down right next to an updraft, so they go back up again. And eventually they keep freezing up here to where they get pretty big. And eventually the hail's going to be, you're going to see it in a cloud. You can actually see these from dual pole radar, and they actually descend and eventually come out of the cloud. The biggest ones will be in the initial surge. Hail can be 2, 3, 4 inches, even bigger sometimes. Tornadoes are the other problem with thunderstorms. We looked at that severe weather event that occurred the other day, and there was at least 24 tornadoes on the ground at that time. If I go back to that event here, and this is supposed to be coming up to the tornadoes that occurred in Mobile, Alabama for one of them here. What I wanted to show you was with that one. Here is when they issued the warning. And that warning right here is the tornado. You see how there is some very strong rotation right in here. There are two different collars basically next to each other, and they're very bright. That indicated the wind that was coming here. And you can see it's related right here to this thunderstorm. It's not a hook echo yet, but it is a very intense thunderstorm. And this tornado developed on the southern end of it right here and tracked like this. So tremendous wind shear, and the rotation can be seen in the thunderstorms themselves. So one of the last couple things here I just wanted to go over a little bit is where you think these tornadoes might occur, and most of them do occur down towards Texas, Oklahoma, Kansas. But notice, you get some up in here. In Ohio, get some, especially the southwestern corner of Ohio. Much higher probability than the northeastern corner of Ohio. And this, for example, is the Joplin tornado, which occurred a few years ago, was an EF5. And here's the scale we use. The EF scale was generated in consultation between meteorologists and civil engineers by looking at damage. Civil engineers, when they look at damage to buildings, trees, can estimate the force that occurred. And they related that to wind speed. And we were able to take that then, make a scale of wind speed, and relate it to damage. When you go out in the field to do an evaluation for how strong a tornado is, an EF scale, you're looking at things like trees, you're looking at buildings, you're looking at how sound the structure was built, how much damage there was to a car, for example. All these different things. There's literally about 300 slides, pictures that we can look at to estimate what the wind speed is. And we go through the whole entire damage path to do that, to determine whether it's an EF0, and if it changed to an EF1 or 2, or even all the way up to an EF5. And here you can see tornado. I say a hook echo typically. The one I showed you earlier did not have one. And here's the wall cloud. Wall cloud is basically very rain, cooled air from next to it is being pulled up and into that section of the cloud so that the cloud becomes flat and low. And if you look at it, there was a drone footage the other day that would have showed it perfectly. You can actually see a very flat looking cloud well below the base of the cloud around it. And if you see that, you know you have potential for tornadoes. So I hope you got a little bit out of this. Please let me know if you have any questions.